Hey guys, so this is notes 4.4 and 4.5. This may be a little longer one because the oxidation reduction reactions, aka also known as single displacement reactions, the ones that we've been working with as far as, like, in case you forgot what a single displacement reaction looks like, it might be something like nickel plus copper chloride. Then the nickel is a metal, and because the activity series, you guys all remember this, right? Copper's number 22, nickel is number 7, no, it's not 17, that's lead. I don't know what nickel is, but it's less than 22, which means that nickel is more reactive. So nickel then takes the place of copper like this, and copper's out by itself. Here is an oxidation reduction reaction, a very simple one, because here nickel has zero charge when it's by itself. All elements, when they are by themselves in a chemical reaction, have zero charge. It doesn't matter if it's Cl2 because of Brinkelhoff, it still has zero charge. They are neutral atoms, and then when they are over here in the compound, like this one is, it has a +2 because chloride has a -1 when it's in a compound. And then the 2 is here because of crisscross. So all the stuff that we've learned before is what we're talking about now, and now I'm just giving it specific names, such as oxidation. In this case here, the nickel goes under oxidation from one side to the other because it loses electrons. In this case, actually, it loses, I should make that a minus, it loses 2 electrons as it goes from the left-hand side to the right-hand side. It loses 2 electrons, that's why it gets a positive +2 charge. So when you lose electrons, you gain a positive charge. So I like to think of oxidation reduction in terms of a very simple number line. If you move to the right, whereas you lose electrons but gain positive charge, then that is oxidation. Okay, so oxidation moves to the right like this. If you're moving to the right, or if you're moving to the left, then that is what reduction is. Reduction is when you gain electrons and you start to move to the left, where you get more and more negative. More negative is reduction, more positive is oxidation. So nickel here goes from 0 to a +2, that is a positive move in charge. Copper here goes from a +2 to a 0, so that is a negative. So this is the copper is what undergoes reduction, and nickel is what undergoes oxidation. And when we put them together, they're called redox reactions, as in RED/OX, redox, as in reduction oxidation. Okay, so that's just a quick, like a very quick, hey, here's what oxidation reduction is. Oxidation is losing electrons in a chemical reaction, and reduction is gaining electrons in a chemical reaction. So that's, and it's just now talking exactly about that. A substance oxidizes when it loses electrons, which means it gives an electron to someone else. One cannot occur without the other. So if another substance gains an electron, that means it's been reduced, and you can't have one without the other. You just can't have free electrons floating around without a place to be. We have to account for the place to be. Now, oxidation numbers is very simply the charge, okay? That's all it is. You're going to see, again, this is one of those things where there's like 1,000 different names that all mean basically the same thing. If you've ever heard the term valence, this is another common term for oxidation number. Okay, so for oxidation number, that is the same thing as charge and the same thing as valence for what our purposes are. There's a very small difference that is very detailed, and we're not going to get into that. So when we do oxidation reduction reactions, we have to be able to figure out what the charge is of the things that we're concerned about, because if we can't figure out the charge, we can't tell if the charge changed at all. And I think that makes sense. So there are a bunch of rules to talk about how things get a charge. So first of all, there are some really, really easy things, such as when you see sodium by itself, okay, like sodium plus water, we've seen this single displacement reaction, you should know that anything that's by itself has zero charge, okay? It's in what's called the ground state, which means that it's a neutral atom. Protons equal electrons. There is no difference in charge because the plus charges equal the negative charges. Okay. The oxidation number of a monatomic ion is the same as its charge. So that means that over on the other side here, when I got Na, okay, now if you remember what the result of Na plus H2O is NaOH, like this, where the OH is minus and the Na is positive, and then I have H2 here, like this. So this is the, we can get rid of the charges because this whole compound here is 0. So it says that the number of the monatomic meaning one atom ion, such as in this case here, sodium would be a one atom ion, and its charge is +1 and its oxidation number is +1. That's all that means. So this is really simple stuff that you guys have seen before. Let's keep going here. What's the problem? Hang on, let's do this. There we go. So there are some other things. So now we have like metals, nonmetals, when they're not in a compound, it's 0. Nonmetals tend to have negative and positive oxidation numbers. It depends on where they are. Oxygen, here's one thing we can count on. You've heard me say this already. Oxygen is a -2. Okay, we're going to stick with -2 no matter what. Sometimes there's something called peroxide. You've heard of hydrogen peroxide before. Hydrogen peroxide, oxygen is when it has a 2 and a -2. That is peroxide. Okay, you will see that in the name for this to be the case. If you just see oxide though, okay, we're talking about a -2 for oxygen. So that's the key to remember. Oxide is -2, always. Hydrogen is only a -1 when it's bonded to metals such as sodium. So you can actually bond hydrogen like this. This would be sodium hydride. Okay, this actually happens. The sodium always has a plus. There's no exception for that except when it's by itself as Na, as like sodium metal. In a compound, doesn't matter what the circumstances are, sodium has a +1 when it's in a compound, and in this case, that means hydrogen has the -1. Sodium's a cation always, and hydrogen in this case is an anion. Under other circumstances, though, hydrogen then would have the +1, just like it does in hydrochloric acid or hydrogen chloride. It has a +1 when it's with a nonmetal. It has a -1 when it's with a metal. That's how hydrogen works. Most 90%, 95% of the time, though, we're going to see it like this, where it's a plus, hydrogen. So get used to seeing a +1 for hydrogen. Nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. We'll talk about that. Here's one thing that we always know. If you see anything that has fluorine in it, it's always a -1. Fluorine is a minus. It can't be anything else because it's the most electronegative element that there is. So it pulls electrons in, so it must be the -1. The other halogens, though, have positive oxidation numbers. So they're a -1 when, just like you saw sodium fluoride, in this case sodium chloride, which is another halogen, which is another halide, whatever you want to call it, either of those two names works. Like that is good, it has a -1 like we always think it does, but then when you see it in a polyatomic ion, like ClO, this would be hypochlorite. In this case here, oxygen has a -2. That means that this, if I get rid of, now we're going to take a look at the polyatomic ions. I'm getting a little bit ahead of myself. But if it's in a polyatomic ion, that's what oxyanions is. It means polyatomic ion, okay? Oxyanion is a polyatomic ion. So let's keep moving forward here. So the sum of the oxidation numbers in a neutral compound is 0. We know that. We know that H2O, has 0 here because I have a +1 and there's 2 hydrogens, and the -2 for oxygen, and there's only one of them, and that's where that 2 comes from. Crisscross is how we keep compounds 0. So a compound is 0 in charge, and that's how we figure out the different parts of the compound, what their charges are. The sum of the oxidation number in a polyatomic ion is the charge of the ion. So let me go back to the situation we had before when we have sodium hypochlorite like that, and we just take a look at just chlorite itself, which is hypochlorite, which is ClO with a -1 charge. When I break this down, oxygen is always a -2, okay? The oxygen plus the chloride, the chlorine, is going to equal a -1. So what actually finishes this like math equation? The math equation is very simply something plus a -2 equals a -1. And the answer to that, of course, is a +1. So in this case, the oxidation number for chlorine would be a +1, because that's what makes this math sentence correct. Because a +1 plus a -2 equals a -1. Where did I get this from? This is the charge of the polyatomic ion. Okay, just like when we have something like this, where we have the compound, I have a +1 for hydrogen, but because there are two of them, I actually have a total +2. I wrote that really ugly. Let's try this again. A total +2. Plus, and then we know that oxygen's a -2, and that's how we get 0 for the whole compound. Okay, so we do the same thing for the compounds, except when it's a compound, it's always 0. When it's a polyatomic ion, it's always the charge of the polyatomic ion that we get them to equal to. So now we can find the oxidation numbers for anything that's in a polyatomic ion. Let's keep going here. So let's do a couple of these. This is CO3. This right here is, of course, a polyatomic ion, so that means the CO3, and whatever happens here, it's going to be carbon plus oxygen is going to equal the -2. It has to equal whatever the charge is. If I have 3 oxygens and each one is a -2, that means what I have here is a plus or a -6. So my negative for this is a -6, because 3 times a -2 equals a -6. The question is, what is the oxidation number for carbon to make this true? And of course your answer then, of course, would be a +4. Okay, so carbon's a +4 here for its oxidation number. Oxygen is a -2 for each one of those oxygens, and that's how we get the -6, and that all equals the charge of the polyatomic ion. That's how we do all of them. So go ahead, if you would, go ahead and tell me, like, I want you to, on this piece of scrap paper, I'm going to give you a second here, I'd like you to see if you can find nitrogen here, if you can find iron here, and if you can find sulfur here. Okay, go ahead and pause this. I'd like you to try this on your own and see if you can do it. If you have no idea, then I guess just hang on. Okay, and we're back. So let's take a look at this now. I'm going to do them right down the row here, starting with the FeCl3, I mean. So this is a compound. I know it's a compound because I don't see any charges, right? So this is FeCl. There are 3 of them here, and I know that whatever I get here and here, the positive and the negative, is going to equal 0. That's what I know about compounds. I know that the Cl, each one of these Cl's has a -1. Times 3 gives me a -3. That's how I get the minus part of this. That means that Fe must have an oxidation number of +3. Okay, remember that the oxidation number and the charge are the same thing. So that's the answer to that one. So that's a +3 for iron. Now this one is a polyatomic ion. So if I rewrite this here, NO3, that's all going to equal a -1. So I know oxygen is always a -2, which means I got a -6, just like that. That means to get the -1, I must have a +5. So nitrogen in this case is a +5, just like that. +5 for nitrogen. SF6, so SF6 looks like this. We know, according to the rule, that fluorine is a -1 always, so that means that I have a -6 like this. This is a compound, so it equals 0, which means that sulfur in this case must be a +6. Excellent. Okay, I hope you got the same answers as I did. I hope you understood how you got the answers following the simple rules that were given. Okay, let's keep going. Let's try this again. Displacement reactions are exactly what we talked about. This is going to only talk about, look, this is 22, 24, right? This one works. It goes from 0 here to a +2, which means the Cu is oxidized. So this right here is oxidized because it gains a positive charge. The +1 here to here goes from a +1 to 0, which means it's gaining electrons and gaining a negative charge, which means reduced. So oxidized and reduced, okay? We don't have to label them like that yet, but that's what this, guys, this is a single displacement reaction. That's all this is, single displacement reaction. You know all about them, okay? The reverse reaction does not occur. Why doesn't that occur? Because this right here is not reactive enough to displace this one. We talked about that already. You guys are already all over this. The activity series is basically the same one that I showed you before. They're missing one here. I think strontium is usually placed up here in number 4 spot, like right there. But because they didn't list it in there, these are all off by 1, but that's fine. It doesn't make a difference. We'll use the one that I gave you in the equations test handout or equation test sheet. But this is the activity series, like still the same, doesn't change anything. The two solutions can maintain the same so this is molarity. So what is molarity? Molarity, M, equals moles of solute divided by volume. Okay, my volume almost always is going to be in liters. So get used to this equation. We're going to use it a lot. This is a way of measuring concentration. Okay, so concentration is how much stuff is mixed in the water. That's what it comes down to. It's very simple. How much stuff, it's like, did you put 4 scoops of salt in the salt water, or did you put 8 scoops of salt in the salt water? Okay, we could measure the mass of the salt before we put it in the water, find the number of moles now that you can do that conversion from mass to moles for sodium chloride, and then you would use whatever that conversion is to find the number of moles, and we can figure out how much the total volume is. Is it going to be half a gallon, or 2 liters, or whatever it is? Okay, so that's how we do a concentration. It's actually pretty straightforward. Mixing a solution is something that if we had way more class time, you guys would be mixing solutions so that we could go through titration, which is something we're going to see later on. So dilution is when you take a concentrate. You can see this right here. That's a stock solution. You take a certain amount. That's called a pipette. The pipette is a way to measure accurately a certain amount of liquid, and then you move it over. This is transferring the liquid in the pipette like this, and then over here you fill the rest of it with water. And that means pure water, and that means that you'll notice a difference in the color, meaning that this is the diluted solution, okay, and this is the concentrated solution. Okay, so that's all dilution is taking a piece of a concentrated solution and then filling it with water to get a different, less concentrated, less, lower molarity is what we're talking about. That's dilution. Usually, and I think you should write this down, usually when we do a dilution reaction, you know how it's molarity equals moles per volume, like this. And if I rework this algebraically just to find the number of moles, what I get then is, is molarity times volume. That's what happens when I solve for moles. If I keep the moles the same but change the volume and the concentration, I end up with an equation that looks like this. Okay, M1 and V1 are the more concentrated and the lower volume of my number of moles, and that equals M2 V2, which is the diluted side. Over here is the diluted side, which means lower concentration but higher volume. So this is our working equation for dilution. They'll have to give you 3 out of the 4. They'll give you a concentration, they'll give you a volume they're looking for, and a concentration that they're looking for. And you would have to figure out how much of the original stock solution you would use. That would be the V1. How much would be volume? Okay, and we'll see some of those. We're going to practice those problems for 4A, I believe, possibly 4B. And we'll get to that. We need to get to that. Maybe not before the end of the trimester. We'll have to start maybe on 3rd trimester when I see you guys again. Yep, you'll get a break. Okay. So I think that's it. I think now we just go right into titrations from here, and I'll talk more about this later on. The next slide is titration. So that's it.